All right. So now that we've established the concept of a species, we now have to talk about, well, what do we do with species? Why, as scientists, do we want to define a species concept? And as we talked a little bit about earlier in the module, a big part of defining a species is to figure out its evolutionary origins and how it's related to other living things or even extinct things, formerly living things. And the practice of classifying species and then putting those into a hierarchy and talking about their evolutionary relationships is known as taxonomy and systematics. And so in this lecture, we're going to talk about those things because later in this course, we're going to be talking about classifying fossils into species, classifying those species as part of a genus, and then how all of these things are related to each other in evolutionary time. And we do that through these two practices, taxonomy and systematics, which is why it's really important that we talk about them. So taxonomy is, at the end of the day, just the science of how we recognize and organize biological diversity. So as I've mentioned in previous lectures, there's a shit ton of species on planet Earth. And evolutionarily, there's a shit ton more species. So as scientists, we need to take all of this diversity that's on the planet today and that has ever existed on the planet. And we need to figure out, how do we organize it? How do we make this make sense? And so what we've done is we've taken all life forms, past and present, and we've ranked them into a hierarchy. And I've already talked about this hierarchy before, and it's likely that you already have a decent understanding of what this hierarchy is, because that hierarchy is going to be kingdom, phylum, order, class, family, genus, species. Now, the practice of systematics is very similar to taxonomy. It just does a little bit more. So taxonomy is literally just, let's throw organisms onto a hierarchy. Let's say they belong to this kingdom, to this family, to this class, to this order, et cetera, et cetera, et cetera. Systematics then takes that hierarchy and also starts to define evolutionary relationships. So systematics is the way that we know that a jaguar is more closely related to a lion than it is to a chimpanzee. Systematics is how we take those hierarchy and we make it make evolutionary sense, where every organism that's in the same family is more closely related to each other evolutionarily than they are to an organism in a different family. So systematics and taxonomy are very closely related practices, but they are slightly different practices. Right? But these two practices are important because, one, they do reduce that complexity of life. They do take the thousands and millions of species that exist and have ever existed, and they help us make sense of them. And a lot of the time, science is all about taking diversity on planet Earth and helping it make sense to us as humans. And it also helps us figure out those evolutionary relationships. Because again, if you're all in the same family, or you're all in the same genus, or you're all in the same class, or the same order, or the same kingdom, that is supposed to indicate something about evolution. Because the more closely you related you are, and where you're placed on the hierarchy, the more closely related you are in evolutionary terms. So these two practices are going to be helpful for us. And they're going to be helpful for us in our study of human evolution, because there's a bewildering amount of diversity in our evolutionary lineage, just of the humans and the hominins. And so this is going to help us reduce that complexity down to help us understand the evolutionary story of hominins and modern humans, and also help us understand those evolutionary relationships between them. Now, the person that we go back to, the person who started all of this off, is Linnaeus. He is the father of modern taxonomy. He is the one who established this system of kingdom, phylum, order, class, family, genus, species. He is the person who established that we name species based off of their genus name and their species name. So we are Homo sapiens. Gorillas are gorilla. Orangutans are Pantroglodytes. They are the ones that established that, right? Like, he's the one who said that you have your genus name and your species name, and combined, that's what your name is scientifically. That's what we call binomial nomenclature. And so Linnaeus is the one who really gave us this classification of animals and plants. As you can see here, this is the classification for wolves that you see on the screen right now. So you define species, all things like that. So it's wolves on the one side of the screen, it's humans on the other side of the screen, and species, genus, family going up into all of life form. So he's the one who really first defined this. And this is what taxonomy is really all about, right? And then binomial nomenclature, as I said, is that every species needs its own scientific name, and we describe them using two names, the genus and the species. And when we write them out, they're always italicized. If you're writing it handwritten, you always underline them. That indicates to people that you are using the scientific or scientific name. And the scientific or name, the binomial nomenclature, is important because we use this name universally around the world, no matter what your language is. We as humans are Homo sapiens, no matter what language you're speaking. Chimpanzees are pan-troglodytes, no matter what language you're speaking. I did think I said I misspoke, and you said that that was orangutan earlier. Now that I'm thinking about it, it is chimpanzee. I'm sorry that I misspoke earlier. Orangutans are Pongo pygmaeus. So that's really helpful. The other thing too is that while languages change and how the names of like the common names like chimpanzee or orangutan, those can change over time as language changes because language is always changing. These species names are fixed. The rule of binomial nomenclature is that you cannot change a name. Once the name is there, once it's in place, you cannot change it. It is what it is, no matter what. All right, so these two things really help us out because it gives us a universal way of species names that doesn't change based on language or culture. And two, it's a fixed name and that you always have to use the first name that's established. So when we classify animals based off of kingdom, phylum, order, class, family, genus, species, as we talked about before, when we were talking about species, Linnaeus, because he predated evolution, was really all about morphological features. So he was always saying that you need to classify living things based on how similar or different they are in terms of their morphological features. Now, one of the really important things for this is that you have to be clear about what features you're going to use to distinguish between different animals. So for example, if you're like, okay, I have a human, I have a lion, and I have a fish. Saying, well, we're going to look at how many eyes do they have isn't super helpful there because all three of those species or all three of those organisms have two eyes. So essentially, you're going to classify humans, lions, frogs, and fish all into the same group. And so that's not really helpful. Now, two eyes is going to help you distinguish between humans and insects, but it's not going to help you in that earlier setting. So we have to be very careful about what features we are going to use when throwing and classifying animals into their kingdom, their phylum, their order, et cetera, et cetera. All right. Now, the reason we have to be careful about this is because, as I said earlier, one of the reasons that we do classification, one of the reasons we do taxonomy and systematics is to distinguish evolutionary relationships and to determine evolutionary relationships. So we have to be careful when picking traits because, again, what Linnaeus was saying to us is that two animals that have more common physical traits are more closely related to each other than animals that don't share a lot of traits. But the problem with this is that sometimes traits can be similar because of similar evolutionary origins. So the reason lions have two eyes, humans have two eyes, and frogs have two eyes is because we all share a common ancestor. So we all inherited having these two eyes from our common ancestor. When that happens, we call that homology, right? These are when we see different species share similar traits because they inherit those from a common ancestor. And those are the traits we're looking for. We are looking for those traits because those traits are going to help us determine evolutionary relationships, which are going to help us determine that hierarchy of taxonomy that actually reflect evolutionary origins, which a good taxonomy does. What we have to be careful about is that we have to avoid analogies. We have to avoid traits that independently evolved with each other, not because they share a common ancestor, but because they are evolving to deal with a similar problem. So, for example, we know that birds have wings and bats have wings, but bats are mammals. Bats are more closely related to us humans than they are to birds. They only have wings because they evolved wings independently because flight gives you certain advantages. Getting food, escaping predators, finding habitats to sleep in and live in, right? So what we call this is analogy or convergent evolution. This just means that you're developing similar traits because they are evolutionarily advantageous to you, but you don't share a recent common ancestor. We don't want these in our taxonomies. We do not want analogies because that's going to make it confusing. Because if we accidentally use wings, we would classify bats and birds being more closely related to each other than either is to a lion. But we know that bats and lions are more closely related to each other than either are to birds. So we really want to be careful with that, right? So what we are looking for is homologous traits, right? These are traits that are similar because they are from the same evolutionary lineage. So we know that most mammals, reptiles, and amphibians have a similar structure in their limbs. So we call this the 1-2-some-many system. So if you look at your upper limb, you have one bone here. This is the humerus. In your lower arm, you have two bones, the radius and the ulna. You have a bunch of bones in your wrist, and then you have a ton of bones in your hand. Pretty much all mammals, amphibians, and reptiles will have this structure because our common ancestor, the first organism that crawled out of the ocean and lived on the land, has this same system. Right? Now, animals that are more closely related to us than like fish also have this system. Whales, dolphins have this system because they evolved out of land mammals that went back into the ocean, right? So this helps us figure out evolutionary relationships because this tells us that whales and dolphins are more closely related to us than they are to fish because they have this system, because they're homologous, because we inherited this from a single common ancestor, right? This is different than analogous traits, which have the same function, but a different structure. So we know that bats are not related to birds because they both have wings, but bats, as you can see in this picture, have this 1-2-some-many system to their limbs. This shows that they're more closely related to reptiles and mammals, which also share this feature, unlike birds, right? So bats and birds do not reflect a common ancestry because this is convergent evolution. They both evolved wings independently from one another, not because they share the same ancestors. So again, to repeat myself and to emphasize a point, when we construct taxonomies, we only want to use homologous traits because those reflect common ancestry. All right, we're going to hit this again and again and again when we talk about human evolution, because we're going to keep running into the issue that when we classify evolutionary relationships, we are looking for the greatest number of homologous traits. We do not like analogies in evolution. Those confuse us because they do not reflect common ancestry. Right? So for the most part, we're not concerned with analogous traits in this class. We're going to look at some traits that are analogous, but we're going to talk about why those become confusing and why they're problematic and why we don't want to look at them too closely. But most of the time, what we're looking into this class is homologous traits. And the nice thing about homologous traits is that they can be further divided into primitive traits and derived traits, and those are going to help us even further. So primitive traits, when we talk about primitive homologous traits, those are ancestral traits. This idea of primitive just means old. It has nothing to do with inferior. So I know when we talk about human cultures, we're like, that's a primitive belief system, and that's like a judgment call. We're not doing that here. Primitive here just means old. So essentially, the primitive trait is the trait that has existed in an evolutionary lineage for a very long time. So most primates monkeys, apes, etc., have 5 digits on their hands. So we have 5 fingers, 5 toes. And that's pretty common, right? This hasn't changed for a very, 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 very long time in the primate lineage. So having 5 digits is primitive in this evolutionary lineage, right? Because it's been there, it's at the base of primate lineage. Now, the opposite of primitive traits are derived traits. These are traits that are newer in evolutionary history, right? So if we talk about digits, horses only have 1 toe, right? That's the hoof. It's 1 toe. They used to have 5 toes, like most other mammals. They lost those. So 1 toe for the horse lineage is a derived trait because the ancestral trait, the primitive trait, is 5 digits, 5 toes. Horses have 1 toe that's unique to them. So that's a derived trait. So primitive traits are the older traits in an evolutionary lineage. Derived traits are the newer traits that distinguish species and genera from other species and genera that are closely related to them. So as you can see here, we can follow the horse evolution. Equus is the modern horse. Hyracotherium is the ancestral horse. Having 5 toes like this is primitive, and having 1 toe is derived. And they evolved this because it makes that 1 toe easier to hold a lot of that weight and on that 1 hoof, right? So we see that there were 5 toes, and then we lost some of those toes, and we lost more of those toes. And as you can see from the letters, like from the Z and the W and the Y here and the X, in Equus here, you can see where all those toes, those bones still exist. They didn't just completely disappear, but they became a lot smaller through evolution and as they gained 1 toe. In the primates, having a tail is primitive for primates, but humans don't have a tail. So the loss of a tail among the great apes, including us, is a derived trait. So if you have questions about this, please feel free to ask it in the office hours channel in Discord. But again, primitive traits are the older evolutionary traits. Derived traits are the newer evolutionary traits, right? So if we do not see any change from a common ancestor to the species that comes later, it's a primitive trait. If there is a change from the last common ancestor, it's a derived trait. So we and chimpanzees share a common ancestor. That common ancestor walked on 4 limbs. Chimpanzees still walk on 4 limbs. That is a primitive trait. Humans walk on 2 legs. That is a derived trait because it is a change from our last common ancestor with our closest living relatives, the chimpanzees. Right? So what we know is that if a trait is common among closely related organisms, it's a derived or it's a primitive trait. So chimpanzees walk on 4 limbs, gorillas walk on 4 limbs, monkeys walk on 4 limbs, orangutans walk on 4 limbs, but baboons walk on 4 limbs, bonobos, all of these walk on 4 limbs. So a majority of the primates walk on 4 limbs. So walking on 4 limbs is the primitive trait. Only one of these species walks on 2 legs. That's us, Homo sapiens, modern humans. That is the derived trait because we are the only ones that have this, right? Now, when we're trying to figure out if a trait is primitive or derived, it's helpful to look at an outside group. So when we're looking at humans and chimpanzees, and we're like, okay, chimpanzees walk on 4 legs, humans walk on 2 legs. Which of those is primitive? Which of those is derived? Well, bringing it in monkeys will help, right? Because we can look at monkeys, which are related to us, but further back in evolutionary time, they walk on 4 limbs. That can help us determine that, 4-legged walking, quadrupedalism, is the primitive trait, and bipedalism, walking on 2 legs, is the derived trait, right? And you could go further and further back and say like, lions walk on 4 limbs, cats walk on 4 limbs, dogs walk on 4 legs. You can bring in outgroups, and those will help you figure out the primitive traits, because the more traits that an outgroup shares, the more primitive it is likely to be. Right? So the other thing to keep in mind is that primitive and derived are relative terms. So if we're just talking about us and if we're talking about tails, tails are derived, or no tails are derived because primitive traits is the tail, right? But if we're just talking about us and chimpanzees, then all of a sudden, what is primitive and what is derived changes. So we're looking at all life forms that have ever lived on planet Earth. The primitive trait is like being a unicellular organism, right? But if we're looking at just these species, all of a sudden, what's primitive and what derived starts to change. So this is relative, depending on, are you looking at just an individual lineage or a much wider lineage, right? So again, loss of a tail is a derived ape feature. Quadrupedalism is a primitive primate feature, right? So again, newer traits are derived, older traits are primitive, but it depends on the scale that you're looking at, right? Here's another way of looking at it, right? So why do we care? Because this is what helps us determine evolutionary relationships with one another. So there's two ways of looking at and reconstructing evolutionary relationships. That's phonetics and cladistics. Phonetics only looks at overall similarities. They don't take into consideration homologies or analogies. The problem with doing this is what Linnaeus was doing. The problem with saying, well, if you have more traits in common, then you are more closely related to each other, is that if species are having a lot of analogies, if there's a lot of convergent evolution going on, like with birds and bats, you are going to mess up your evolutionary relationships. This is why we, in human evolution, do what's called cladistics, which is that we only look at derived homologous traits when determining how closely an organism is related to another organism. We don't look at primitive traits. We don't look at ancestral we don't look at analogous traits. We only look at shared derived traits because we are looking at what we want to know, what new features appear in an evolutionary lineage, and that's what's going to help us determine these evolutionary relationships. Right? Now, this can cause some problems because what we assume in cladistics is that there are no parallel evolution or evolutionary reversals. We assume that any new trait is because it's a derived homologous trait. That traits can't go backwards, that traits are only going forwards. Now, we know this isn't true because, for example, even in the evolutionary lineage of humans, from the time we diverged from chimpanzees till today, we know that tooth enamel has gone back and forth. We know that tooth enamel has gone thicker, then it's gone thinner again, and it goes thicker, and then it goes thinner again. It goes thicker, and it goes thinner again. This makes it difficult because that means that enamel thickness isn't super helpful for us in determining evolutionary relationships because there's really no way of dealing with this with cladistics. So we just throw it out, right? Because again, cladistics assumes traits only evolve once and they only evolve in one direction, even though this isn't true. We only assume this because it makes it a little bit easier, right? It makes it a little bit more convenient. And we just don't deal with traits that don't follow this rule. Right? The other problem with cladistics is that it really relies on dichotomies. It really relies on, do you have a trait or you do not have a trait? But things like enamel thickness, tooth size, the coat of fur or hair, those don't exist in a binary. But cladistics either wants it to be this or that, because that's how we determine things. So when you're like, how closely related is species A to species B? Well, let's count their traits. Are they brown or black? Do they have 3 toes or 2 toes? Do they have wings or no wings? We don't really know how to deal with the fact that it's like, well, is there enamel thickness 1 millimeter, 2 millimeters, 3 millimeters, 4 millimeters, or 5 millimeters? We really don't know how to deal with that, right? So cladistics isn't perfect, but it is the best thing we've got because it controls for analogous traits, it controls for convergent evolution. It isn't just about how similar organisms look, but how many shared derived traits do they have? And this is how we know that like cockroaches are related to shrimp and whales are related to humans, even though cockroaches don't really look like shrimp and whales really don't look like humans. But it's because we're counting the number of shared derived homologous characteristics that get us this. It is the most reliable way we can classify organisms and their evolutionary relationships. And this is what we do in human evolution. Right. So I know that was fast. I know this can be confusing. I've assigned some readings and other guides to help you out. But again, please use that Discord channel, that office hours channel. Please ask as many questions as you want. I will be more than happy to jump into those questions whenever I see them. And I will jump in and I will answer anything that's still confusing to you.